I'm going to define for you a particular type of function called a sequence. Now, we're accustomed to functions, lots of different types of functions. For example, we're accustomed to linear functions. There's a linear function, and we know that the domain of this linear function is all real numbers. And we can plug in values here. I could plug in a -1, I get -2. I could plug in a 1/2, and I get 2 times 1/2 is 1. I could put in a 2, I get a 4, you know, 3/2, I get a 3, and so forth. I could put in a lot of different values. Put in a 4, get an 8. The fact is, the domain of this function is all real numbers. Now, what if we say, I'm going to limit the domain of this function to only be, I want the domain just to be the positive integers. In other words, if we restrict the domain and we say, okay, I'm going to make it so that these values here are not going to be part of the domain. I'm only going to use the positive integers, 1, 2, 3, and so forth. So, so we make it this, we say, okay, there's our domain, the set of positive integers. That, when we do that, we have, the type of function we have is called a sequence. Now, usually, we're not going to write a sequence using this type of notation, f of x. Usually what we'll do is we'll use a sub n or b sub n. Usually it's a lowercase letter, a, b, c, and we use a subscript. So instead of saying f of x equals 2x, we might say a sub n equals 2n, like that. And then we can evaluate this function. So I might say, well, what is a, what happens when I plug in a 1? Well, it's a sub 1 equals 2 times 1, which equals 2. So we're just limiting, and we could do that to a lot of different functions. We could have, well, what about this function? What if we have b sub n equals n squared? You know, that's like f of x equals x squared, but we have b sub n equals n squared. And we could talk about, I want the third term of this sequence. Well, the third term of the sequence would be what happens when we just plug in a 3. But what you're not going to have is a sub 3/2 or something like that, or a sub -1, something like that. That's not going to be a sequence. If we're dealing with a sequence, the domain is the set of positive integers. So in this case, b sub n equals n squared. If you look at the graph, okay, let's just look at the graph of x squared. Let's suppose that we have f of x equals x squared. Okay, and here we have b sub n equals n squared. If you look at f of x equals x squared, of course, we know what that looks like. It's just a parabola. Okay, very, very common graph we're familiar with. So there's what the graph looks like. Now, if you look at the graph of the sequence, it's not continuous. It just has values at the integers. So we have 1, 2, 3, 4, and so forth. And its graph would look like this. Well, let me use this. We've got a value there, value there, value there, and so forth. So it would be just some points, some dots like that. So the graph is going to look different. It's not going to be continuous like maybe x squared. It's going to have just dots. Now, not all sequences are given to you in a formula like this, like this one, where we have b sub n equals n squared. Not all the time do you have to have a formula. Sometimes you'll be given a list of values. For example, we have this b sub n equals n squared, and you've got a formula for it. Well, it wasn't necessary that you're given a formula. You may have been, there are times when you're going to be given a sequence like this and they'll just list. And so in other words, we know that B1 is equal to 1, B2 is equal to 4, B3 is equal to 9, and B4 is equal to 16. So we can calculate those. So if you're not given a formula, so we're not given b sub n equals n squared, sometimes you'll be given just a list of the values, like this, okay? In other words, you don't have to have a formula to have a sequence. This is just a listing of the values, okay? And sometimes you'll be asked, well, to come up with a formula, if you have the first term is 1, the second term is 4, and so forth, and you'll be asked to find that b sub n equals n squared. Now, there's another type of sequence that you'll encounter, and that's a recursive sequence. So let's look at an example of that. Let's suppose that we have something like this. Let's suppose that we have um, a sub n plus 2 equals a sub n plus a sub n plus 1, something like that. And in this case, what you need to know is you need to know the nth term and the n plus first term. So let's suppose a sub 1 is equal to 1, and let's suppose a sub 2 is equal to 1 as well. And you want to find a sub 3. In other words, we're saying, well, what happened? Let's see where we can begin. We can begin when n is 1. So when n is 1, a sub n plus 2 is a sub 3. So let's see what we've got now. So a sub 3 is equal to a sub 1 plus a sub 2. And let's see what we have then. Now we have a sub 3 is equal to 1 plus 1, which is equal to 2. So you can see that we're starting to have we're starting to be able to generate some terms. Notice we have that the first term, a sub 1 is 1, a sub 2 is 1, and then a sub 3 is 2. Yeah, start to make a 3. There we go, a 2. Now we want to get the fourth term. So let's see here. A sub 4 is equal to a sub 2 plus a sub 3. Now, remember, a sub 2 is equal to 1, okay? So this is 1 plus a sub 3 is right here. That's 2, and we get a 3. So I'll put a 3 in there. Now, you don't have to manually go through this every time. What you see is happening here is if you want this term, you need to add up the previous 2 terms. So it looks like that's the way this works. So this next term here would be 2 and 3 is 5. The next term would be 8. The next term would be 13. And you can see it just goes on and on. You're adding up. To get any particular term, you're having to add up the previous 2 terms. And that is a recursive sequence. So there's not a lot to this so far. I mean, we say, okay, here's what a sequence is. It's a function with the domain limited to the positive integers. And then we take note of some special things like, the different ways that you can see sequences presented to you, a list or recursively. And another thing that I want to take note of is one of the things that comes up when you're working with sequences is factorials. We haven't worked with factorials in calculus up to this point, but we're going to work with them now. They're going to appear from time to time, but remember what a factorial is. We define 0 factorial to be 1. I'll just refresh your memory. We've got 1 factorial to be 1 as well, and we've got 2 factorial. Now remember what a factorial is. You just start at the number and you count down in integers in multiplication. So 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And we could keep going on and on. I'll just jump over here just so you can clearly see this is 5 times 4 times 3 times 2 times 1. That's 5 factorial. Mainly, remember 0 factorial is 1. Sometimes that's a little bit counterintuitive. But this is what a factorial is. Now, oftentimes, we'll be working with a sequence, and it will be something that looks like this. maybe n factorial over n plus 2 factorial, like that. Now, we could leave it like that and work with it. I mean, we could plug in values and evaluate it, but sometimes it's easier if we simplify it. So what I want to show you is, well, how do we simplify an expression like this, n factorial over n plus 2 factorial? Well, here's what you can do. You can recognize that n plus 2 factorial, I could rewrite that as n plus 2 times n plus 1 times n factorial. I could do that if I wanted. Note this, if I have 5 factorial, I could always write that as 5 times 4 times 3 factorial if I want, and realize that 3 factorial is 3 times 2 times 1. So that's all I did here. I just started at n plus 2 and diminished it by 1 each time, and I write it this way. Now you might say, well, why did you stop here at n factorial? Because up top I have n factorial. And what I was hoping to do is divide those out. So now I have a different expression here. I have, well, a simplified expression, n plus 2 times n plus 1. And there's not even a factorial in that now. But that's how I simplified that uh, sequence that had factorials in it. Now you can do that for different ones. So let's suppose we have b sub n is equal to 2n plus 1 factorial over, let's say just 2n factorial, like this. And we want to simplify that. Well, here we go. We go with the bigger one. 2n plus 1, that's the bigger one. So we have 2n plus 1 times 2n factorial. We're right there. And down here is 2n factorial. So you can see, that cancels out. And now 2n plus 1, well, heck, that looks a lot better than 2n plus 1 factorial over 2n factorial. But that's how we can simplify these. And we could have, you could have something like this. You could have 2n plus 5 factorial over 2n minus 1 factorial. You could have something like that. And this one's a long one, but you could get rid of all the factorials just by saying, okay, this is 2n plus 5 times 2n plus 4 times 2n plus 3 times 2n plus 2, 2n plus 1, 2n, and 2n minus 1 factorial. That's a long process there. I don't know if it's worth it. I'm just trying to illustrate the process. And then you could just cancel those two and you have that mess up top. But anyway, that's the process that you can go through to deal with these factorials. Okay, now let's just look at some sequences here and bring some ideas together. Let's suppose that we have a sequence defined to be this, -1 to the n of 1 over n factorial. Okay, so this is a sequence. And I want to generate the first few terms here. So I'm going to look at A1. Okay, so that's going to be -1 to the first power over 1 factorial, which that's just going to be -1 over 1, or, -1. Okay, now let's look at the second. Let's look at another term here. Let's look at A2. A2 is going to be -1 to the second power over 2 factorial. Now, dig this. -1 to an even power is going to be a positive. So what I'm going to get here is a +1 over 2 factorial, which is 2. So dig this now. We have these terms. We have -1 and we have 1/2. Okay, those are terms that we have so far. Now, let's look at A3. A3 is going to be -1 to the third power over 3 factorial. Or, look, -1 raised to an odd power is negative. And this, of course, is going to be 3 factorial, which is 6. Okay, so we go -1/6. Now, what we have here is an alternating sequence. It alternates negative, positive, negative, and dig this. So look at this. We have our n's, and down here we have our a sub n. Okay, a sub n, and look at how this goes. When we got 1, 2, 3, 4, 5. Now let's just take a minute and dig what's happening here. This is -1. This is 1/2. This is -1 over 3 factorial. Now this next one, we would have -1 to the fourth power. That's 1 over 4 factorial. -1 over 5 factorial. And you'll notice what's happening. With this particular sequence, the odd values for n will give us a negative a sub n. See, this is 1, this is 3, and this is 5. Whenever we have odd values for n, we end up getting negative values for our function output. Now, let's suppose that we wanted to change that. Let's suppose that we want the even values to give us negatives. So how would we do that? Well, here's what we could do. Let me do a different sequence. This is going to be -1 to the n plus 1. See, that way, when n is odd, we add to it and we get an even. So let's see how this works. So this is n factorial. So notice, now when I put in when n is odd, a 1, I add 1 to it and I get an even. So this would give me these values. I've got n and I've got b sub n. And here I go. I've got 1, 2, 3, 4, 5. Now you notice when n is 1, 1 plus 1 is 2. So this first term just becomes a positive 1. The second term, when I put in a 2 in here, 2 plus 1 is 3. Now I'm raising -1 to a third power. So this is going to be -1/2. And this will be +1 over 3 factorial, -1 over 4 factorial, and +1 over 5 factorial. So both of these are examples of these alternating sequences, but we can control which terms get the negatives by raising -1 to either n or n plus 1. So this is something you'll see over and over. You'll see these alternating situations where it goes positive, negative, or negative, positive, and so forth. So this is something we need to be aware of.